August 15th, 1943. 22,000 feet above the Solomon Islands, the tropical sun blazed down on a formation of twin-engine fighters cutting through scattered clouds. Lieutenant Thomas Maguire gripped the control yoke of his P-38 Lightning, scanning the horizon with the practiced eye of a pilot who had already learned that overconfidence in the Pacific theater was a dangerous luxury. The sleek, fork-tailed fighter beneath him represented American industrial might, powered by twin Allison engines, producing over 3,000 horsepower combined. He believed, as his training had taught him, that the key to survival against Japanese fighters was to never turn with them, to use speed and altitude advantage, to boom and zoom. He had no idea that everything he thought he knew about his aircraft was about to change because of a piece of wire no thicker than a pencil. Before we dive into this story, make sure to subscribe to the channel and tell me in the comments where you're watching from. It really helps support the channel. What Maguire and thousands of other P-38 pilots were about to discover would transform the Lightning from a fast but cumbersome heavy fighter into one of the most feared aircraft in the Pacific sky. And it would all come down to a modification so simple that officers initially dismissed it as impossible. The P-38 Lightning arrived in the Pacific theater carrying the hopes of American air commanders who desperately needed a fighter with the range to escort bombers deep into Japanese-held territory. With a combat radius exceeding 400 miles, the Lightning could reach targets that single-engine fighters could only dream of. Its twin-engine design meant redundancy. A pilot could limp home on one engine if the other took damage. The concentrated nose armament, 4 50-caliber machine guns and one 20mm cannon, delivered devastating firepower without the convergence issues that plagued wing-mounted weapons. But the Japanese had the Zero. First Lieutenant Rex Barber, who would later become famous for his role in a critical operation against a high-ranking Japanese commander, sat in the dispersal tent at Henderson Field on Guadalcanal, writing a letter to his wife. The afternoon heat made the paper stick to his forearm as he carefully chose his words. Knowing censors would read everything before it left the island, he wrote about the beauty of the tropical sunsets, about the friendships he had formed with his squadron mates, about how much he missed home. What he could not write about was the gnawing frustration that every P-38 pilot felt when they encountered Japanese fighters. The Zero could turn inside them every single time. Technical Sergeant Mike Daniels had maintained aircraft since before the conflict began, working his way up from prop mechs to becoming one of the most respected technical experts in the 5th Air Force. He had memorized every specification, every tolerance, every quirk of the P-38's complex systems. The fighter's control system used a combination of cables, pulleys, and hydraulic boosters to translate pilot inputs into control surface movements. It was sophisticated, perhaps too sophisticated for the harsh conditions of the Pacific. Daniels stood under the wing of a Lightning that had returned from a mission with combat damage, examining the aileron control mechanism with a critical eye. The pilot, a young lieutenant from Iowa, whose name Daniels had already forgotten, had complained that the controls felt mushy during a turning engagement with Japanese fighters. He had survived only because his wingman had called out the attack in time for him to disengage using the Lightning's superior speed. The problem was not new. Every pilot reported the same issue. At high speeds, the controls became heavy, requiring significant physical force to maneuver the aircraft. The control yoke seemed to fight back against the pilot's inputs, and in a turning fight where fractions of a second determined survival, that resistance was critical. Major General George Kenney, commanding the 5th Air Force, knew he had a problem. Reports crossed his desk daily from squadron commanders, expressing concern about their pilots' ability to engage Japanese fighters in maneuvering combat. The standard doctrine, boom and zoom tactics that leveraged the P-38's speed advantage worked well enough when everything went according to plan. But aerial combat rarely followed plans. In May of 1943, a relatively unknown pilot named First Lieutenant Harold Stumm was assigned to the maintenance test section at Port Moresby. Stumm had an unusual background for a fighter pilot. Before the conflict, he had studied mechanical engineering at the University of Michigan, spending more time in machine shops than most of his classmates. He understood stress loads, mechanical advantage, and force multiplication in ways that went beyond flight school theory. Stumm had flown enough combat missions to know the P-38's limitations intimately. He had experienced firsthand the terror of being in a turning fight with a Zero, feeling the control yoke resist his inputs as the Japanese fighter closed the distance, knowing that his only option was to dive away and use his superior speed to disengage. It offended his engineering sensibility that such a powerful, well-designed aircraft should be limited by something as fundamental as control responsiveness. The solution came to him while he was watching maintenance crews service the aileron control system. The ailerons, the control surfaces on the outer wings that made the aircraft roll, were controlled by cables running from the cockpit through a series of pulleys and bell cranks. The system was designed with specific gear ratios to balance control forces throughout the flight envelope. At low speeds, the controls were light and responsive. At high speeds, aerodynamic forces on the control surfaces increased dramatically, and the control system required more force from the pilot to overcome that resistance. Stumm asked himself a simple question: what if we changed the mechanical advantage? He began sketching diagrams, calculating force ratios, measuring cable tensions. The idea forming in his mind was almost absurdly simple. By changing the attachment point of the aileron control cable to the bell crank, he could alter the leverage ratio. Move the attachment point farther from the pivot, and you decrease the force required at the control yoke to move the aileron through the same distance. The trade-off was equally simple. If you reduce the force required, you increase the distance the control yoke had to travel. Pilots would have to move the yoke farther to achieve the same control surface deflection, but Stumm reasoned that pilots would gladly accept more control travel in exchange for lighter, more responsive controls. The modification required drilling a new hole in the bell crank and moving the cable attachment point. The new hole needed to be precisely positioned, measured carefully to maintain control travel within acceptable limits. The change was so minor that it could be accomplished with basic tools, a drill, a reamer, and a piece of safety wire to create a new attachment point. Stumm presented his idea to his commanding officer, who presented it to the group commander, who presented it to the engineering staff at 5th Air Force headquarters. The response was swift and unequivocal. Absolutely not. The official rejection cited numerous concerns. The modification had not been tested by Lockheed, the aircraft manufacturer. It could introduce unexpected stress loads that might cause structural failure. It might create control flutter at high speeds, a potentially catastrophic condition where control surfaces oscillate uncontrollably. The liability concerns alone were sufficient to reject the proposal. Stumm was ordered to drop the idea and return to his regular duties. He ignored the order. Working at night with a small group of trusted mechanics, Stumm modified the control system on his personal aircraft. The modification took less than 3 hours. Drill the new holes in the aileron bell cranks. Move the cable attachment points. Safety wire everything to prevent the cables from detaching. They worked by flashlight, checking and rechecking their measurements, making sure everything was perfectly aligned. The next morning, Stumm took off for what he logged as a routine maintenance test flight. He climbed to 10,000 feet, checked to make sure the area was clear, and began putting the modified aircraft through aggressive maneuvers. The difference was immediately apparent. The control yoke moved smoothly through its full range of travel with significantly less force required. Stumm rolled the aircraft left and right, feeling the response. The Lightning snapped into rolls with an eagerness he had never experienced. He tried a hard turn, expecting the controls to stiffen as airspeed increased. Instead, they remained responsive, requiring firm pressure, but not the exhausting wrestling match he was accustomed to. Stumm pushed the aircraft harder, trying high-speed rolls, reversing turns, maximum-rate maneuvers. The Lightning responded like a completely different aircraft. The heavy, stable gun platform had been transformed into something that could dance. He landed with his hands shaking, not from fear, but from excitement. He knew he had just changed everything. The problem was convincing anyone else. Stumm began with his squadron mates, offering to modify their aircraft and let them judge the results. The first volunteer was Captain William Johnson, a cautious pilot, known for his by-the-book approach to everything. Johnson was skeptical, but he trusted Stumm's engineering background enough to take the risk. After his first flight with the modified controls, Johnson became a convert. He immediately began spreading the word, telling anyone who would listen that Stumm had figured out how to make the P-38 turn with a zero. That claim got attention, but not the kind Stumm wanted. He was called before his commanding officer and ordered to cease all unauthorized modifications immediately. The official position remained unchanged. The modification was not approved by higher authority and violated regulations regarding aircraft alterations, but word had already spread. Pilots who had flown the modified aircraft were talking, and in a combat environment, where survival often depended on aircraft performance, pilots paid attention when someone claimed to have found an edge. Lieutenant Colonel Gerald Johnson, commanding officer of the 49th Fighter Group, heard the rumors and decided to investigate personally. He called Stumm to his office and asked for a straightforward explanation. Stumm brought his calculations, his diagrams, and his test flight notes. He explained the mechanical principles, the force ratios, the trade-offs involved. Johnson listened, asked pointed questions, and then made a decision that would ripple through the entire Pacific Air War. He authorized Stumm to modify one additional aircraft, and Johnson himself would fly it in combat to evaluate the modification under actual combat conditions. 3 days later, Johnson returned from a mission over New Guinea with a Japanese fighter confirmed as defeated in a turning engagement. His after-action report was clinical and detailed. The modified control system had allowed him to match turn rates with a more maneuverable opponent. The increased control travel was noticeable, but not problematic. The reduction in control forces was dramatic and allowed sustained maneuvering without pilot fatigue. Johnson sent his report up the chain of command with a recommendation that the modification be evaluated for fleet-wide implementation. The response from higher headquarters was predictable. Engineering staff raised concerns about unauthorized modifications, liability, safety testing, and adherence to established procedures. The modification would need to be evaluated by Lockheed, tested under controlled conditions, and properly documented before any consideration of wider implementation. Johnson sent back a single-sentence reply. "My pilots are encountering enemy aircraft today, not after Lockheed completes a 6-month evaluation." He ordered his group maintenance officer to begin modifying every P-38 in the 49th Fighter Group. The maintenance crews worked around the clock, processing aircraft as they rotated through scheduled maintenance. Each modification took approximately 3 hours per aircraft. Within 2 weeks, every Lightning in the group had been modified. The results spoke for themselves. Mission reports began documenting successful turning engagements with Japanese fighters. Pilots who had previously relied exclusively on boom and zoom tactics were now willingly entering turning fights and emerging victorious. The psychological impact was enormous. P-38 pilots, who had previously felt at a disadvantage against Japanese fighters, now felt they had a fighting chance in any type of engagement. Other groups began hearing about the modification through the informal pilot network that transcended official channels. Pilots traded stories during brief encounters at forward airfields. Maintenance personnel shared information during supply runs. Squadron intelligence officers compared notes during weekly briefings. The modification became known simply as the Stumm mod, though some pilots irreverently referred to it as the stupid wire trick because of how simple it was. By August of 1943, several P-38 groups in the Pacific had implemented the modification despite the lack of official authorization. The engineering staff at 5th Air Force Headquarters finally acknowledged reality and issued a technical directive officially approving the modification and providing standardized instructions for its implementation. Thomas Maguire, the pilot we met at the beginning of this story, had his aircraft modified in late August. On his next combat mission, he encountered a formation of Japanese fighters escorting bombers toward Allied positions. Instead of making a single high-speed pass and disengaging, Maguire turned with the enemy fighters, using the modified controls to outmaneuver them. He scored his first aerial victory in a turning fight that day, something he had been trained never to attempt. Maguire would go on to become the second highest-scoring American ace of the entire conflict, credited with 38 aerial victories, many of them achieved in turning engagements that would have been impossible with unmodified controls. The modification eventually made its way back to Lockheed, where engineers conducted formal testing and analysis. Their report confirmed what combat pilots already knew. The modification reduced aileron control forces by approximately 35%, while increasing control travel by roughly the same percentage. The trade-off was acceptable for combat operations and actually improved pilot ability to maintain precise control during high-stress maneuvering. Lockheed incorporated a similar modification into production aircraft, though they used a more sophisticated mechanism than a simple cable relocation. But for the thousands of P-38s already in the field, the STUM mod remained the standard modification, accomplished with basic tools and a few pieces of safety wire. Captain Rex Barber, who we met earlier writing letters home, flew his modified Lightning on a critical mission in April of 1943 to intercept a high-value target. The mission required precise timing, long-range navigation over open ocean, and the ability to engage escort fighters while maintaining enough performance to accomplish the primary objective. The modified controls gave Barber the maneuverability he needed to successfully complete the mission, fundamentally altering the strategic situation in the Pacific theater. Technical Sergeant Mike Daniels, the maintenance expert who had initially been skeptical of unauthorized modifications, became one of the most vocal advocates for the STUM mod. He trained other maintenance crews on the proper installation technique, created detailed instruction sheets with precise measurements, and quality-checked installations throughout his group. Years later, he would say that the modification represented exactly what American ingenuity was supposed to be: identifying a problem, developing a solution, and implementing it regardless of bureaucratic obstacles. The Japanese never understood what had changed. Intelligence reports captured after the conflict showed that Japanese pilots reported P-38 performance improvements beginning in mid-1943. They assumed the Americans had introduced a new variant with more powerful engines or improved aerodynamics. The truth, that a simple cable relocation had transformed the Lightning's handling characteristics, never appeared in their analyses. The modification had broader implications beyond individual combat encounters. It changed tactical doctrine for P-38 units throughout the Pacific. Squadron commanders who had previously emphasized strict boom and zoom tactics began teaching their pilots to use the Lightning's newfound maneuverability. Training programs were updated to include turning combat techniques. The psychological impact of knowing they could outturn enemy fighters made P-38 pilots more aggressive and more willing to press attacks. Production statistics tell part of the story. Lockheed manufactured over 10,000 P-38 Lightnings during the conflict. Thousands of them received the STUM modification in the field before the factory-installed version became standard. The modification required minimal resources, basic tools that were available at any forward airfield, and could be accomplished by a two-person maintenance crew in a few hours. The cost-to-benefit ratio was almost incalculable. A few dollars in materials and a few hours of labor transformed a multi-million-dollar aircraft into a significantly more capable weapons system. Harold Stum, the engineering-minded pilot who developed the modification, continued flying combat missions throughout the conflict. He was eventually promoted to captain and assigned to a headquarters position where his engineering expertise could be applied to other technical problems. He never sought recognition for the modification and seemed almost embarrassed when other pilots referred to it by his name. After the conflict ended, Stum returned to Michigan and completed his engineering degree. He spent his career in the aerospace industry, working on aircraft design and development. In occasional interviews, he would downplay the significance of the modification, insisting that he had simply applied basic mechanical principles to an obvious problem. But other pilots who had flown with modified controls knew better. They knew that his simple fix had saved lives and changed the course of aerial combat in the Pacific. The story of the STUM modification illustrates several important aspects of the conflict in the Pacific. It demonstrates how individual initiative could overcome bureaucratic resistance when survival was at stake. It shows how American technical ingenuity operated not just at the industrial and strategic level, but also in the field, where maintainers and pilots identified and solved problems with immediate practical solutions. The modification also highlights the difference between theoretical performance and practical combat effectiveness. The P-38 Lightning had always possessed excellent performance characteristics on paper. It was fast, heavily armed, and had superior range. But those advantages meant little if pilots felt they could not maneuver effectively against enemy fighters. The STUM mod transformed theoretical capability into practical combat effectiveness. Perhaps most significantly, the modification demonstrated the importance of listening to frontline operators. STUM was not a senior officer or a renowned test pilot. He was a lieutenant with an engineering background who paid attention to what combat pilots were saying and had the technical knowledge to develop a solution. The fact that his solution was initially rejected by higher authority but ultimately vindicated by combat results shows the tension that always exists between established procedures and battlefield innovation. The Japanese learned painful lessons about American adaptability throughout the conflict. They entered the fighting with superior aircraft in many categories, flown by experienced pilots who had honed their skills in earlier campaigns. They assumed that technical superiority and pilot experience would continue to provide advantages. Instead, they encountered an opponent who constantly adapted, who identified weaknesses and developed solutions, who refused to accept limitations as permanent. The Zero fighter remained a formidable opponent throughout the conflict, but its advantages in maneuverability became less decisive as American pilots learned to exploit its weaknesses and as American aircraft received modifications that improved their capabilities. The STUM mod was just one of many field modifications that American forces implemented, but it was among the most significant in terms of its impact on combat effectiveness. By the end of 1944, the P-38 Lightning had established a fearsome reputation in the Pacific theater. Japanese pilots learned to respect the twin-engine fighter that could now turn with their most maneuverable aircraft, while also outrunning them and outgunning them. The Lightning's distinctive silhouette became associated with defeat and loss among Japanese aircrew. The top American aces of the Pacific theater, pilots like Richard Bong with 40 victories and Thomas Maguire with 38, flew P-38 Lightnings. Their success was built on superior training, aggressive tactics, numerical superiority, and aircraft that could perform exactly as needed in combat. The STUM modification was a critical component of that performance capability. When maintenance crews gathered after missions to repair battle damage and prepare aircraft for the next day's operations, they took pride in the modifications they had installed. They knew that the wire relocation they had carefully measured and installed might make the difference between a pilot returning safely or not returning at all. That knowledge motivated them to double-check their work, to ensure every installation was perfect, to take ownership of their contribution to combat effectiveness. The modification also created an interesting dynamic between field units and rear-echelon engineering staffs. Initially dismissed and officially prohibited, the STUM mod gained acceptance through demonstrated combat effectiveness rather than through engineering analysis. This reversal of the normal approval process created tensions, but also demonstrated that in combat environments, results mattered more than procedures. After official approval, engineering teams attempted to quantify exactly why the modification worked so well. They conducted wind tunnel tests, flight tests, and detailed analysis of control forces throughout the flight envelope. Their conclusions confirmed what STUM had calculated with basic engineering principles. Moving the cable attachment point changed the mechanical advantage in a way that significantly reduced required pilot effort while maintaining adequate control authority. Some engineers were frustrated that such a simple solution had not been identified during the original design process. Others pointed out that aircraft design always involves compromises, and that control system design in the 1930s had prioritized stability over maximum maneuverability. The modification simply shifted that compromise toward a different point on the performance spectrum, trading some stability for improved responsiveness. What made the modification particularly elegant was its reversibility. If a pilot or unit commander decided they preferred the original control feel, the modification could be undone by simply moving the cables back to the original attachment points. In practice, no one ever requested this. Once pilots experienced the modified controls, they never wanted to go back. The psychological impact of the modification extended beyond individual pilots to entire units. Squadron morale improved when pilots felt they had a competitive advantage rather than fighting at a disadvantage. This confidence translated into more aggressive tactics, more willingness to engage enemy fighters, and ultimately higher success rates in aerial combat. Japanese air forces in the Pacific never recovered the air superiority they had enjoyed early in the conflict. Multiple factors contributed to this shift, including American numerical superiority, improved pilot training, better tactics, and advanced aircraft. But modifications like the Sturm mod played a role by ensuring that American aircraft could exploit every possible advantage. The story raises interesting questions about military innovation and adaptation. How many other simple solutions might have been overlooked because they seemed too obvious or too simple? How much combat effectiveness was lost because procedures and regulations prevented field units from implementing improvements? The answers are unknowable, but the success of the Sturm mod suggests that empowering frontline personnel to identify and solve problems can yield significant benefits. In the decades after the conflict, aviation historians and engineers have studied the modification as an example of effective field innovation. It appears in textbooks on aircraft maintenance, case studies on military adaptation, and histories of Pacific air combat. Harold Sturm's simple idea, implemented with basic tools and common materials, has become a standard example of practical problem-solving under combat conditions. The pilots who flew with modified controls rarely discussed the technical details of what made their aircraft more maneuverable. They simply knew that when they pulled the stick, the aircraft responded. When they needed to outturn an opponent, they could. When they needed to reverse direction quickly, the controls let them do it without fighting the aircraft. That responsiveness, that confidence in their machine, allowed them to focus on tactics and situational awareness rather than wrestling with heavy controls. The modification's simplicity was both its greatest strength and, initially, its greatest weakness. It was strong because it could be implemented anywhere with minimal resources. It was weak because that very simplicity made it difficult for people to believe it could make such a significant difference. How could something as minor as moving a cable attachment point transform an aircraft's combat capability? The question seemed to answer itself. It could not, except that it did. By war's end, the Sturm modification had been applied to thousands of P-38 aircraft across all theaters of operation. While it had the most significant impact in the Pacific, where maneuverability was critical for engaging Japanese fighters, pilots in Europe and the Mediterranean also appreciated the improved control response. The modification became standard practice, something that was simply done to every P-38 as a matter of course. Today, restored P-38 Lightnings, flying at air shows and museums, often incorporate the Sturm modification. Modern pilots flying these historic aircraft report the same improvements that combat pilots discovered 8 decades ago. The controls are lighter, more responsive, easier to manage during aerobatic maneuvers. The modification works as well now as it did then, a testament to sound engineering principles and practical problem solving. And that concludes our story. If you made it this far, please share your thoughts in the comments. What part of this historical account surprised you most? Don't forget to subscribe for more untold stories from World War II and check out the video on screen for another incredible tale from history. Until next time.